Serious game there.
It was very serious. Welcome to the AI Show. I'm Scott Stevenson, co-founder of Deepgram. With me is Jeff Ward, aka Susan. He's a Navy pilot, acclaimed dad joke writer, and AI scientist at Deepgram. On the AI Show, we talk about all things AI. What is it? What can you do with it? How does it affect you? Where is it going? We are live and ready to answer your questions. Comment on YouTube and Twitch, or tweet at DeepGramAI to join in. Today, we're asking the question, the big question, questions. What's the best infrastructure for machine learning? What's the history of it? Where is it at now? And where is it going?
What is the best infrastructure for machine learning?
Good Susan question there. Yeah.
That's what I do. I ask the questions in a different voice.
Yeah.
Because, that really helps.
It does.
Change the voice and suddenly there you go. I mean, seriously. We have seen a revolution recently, and we can point to one of the big enablers, which has been GPUs. We've talked about this a whole lot, but GPUs have not always been here.
Machine learning's been going on for a while.
Yeah.
GPUs haven't been the end all be all of time.
Exactly. I mean, back in the 50s, do you think they had GPUs to crank on? No, they didn't. But
they barely had CPUs to crank on.
Exactly.
I don't think they had that really. They had some kind of calculator type machine
or type person.
Or a person.
Was a person.
Yeah.
But yeah, I mean, the roots of machine learning really goes back to the 50s, and a lot of great experiments on computers of the day starting back there. Minsky wrote his great article describing a lot of these problems in the 50s. So what were the architectures through the ages? And
you have tubes and huge rooms,
a series of tubes.
Yeah, vacuum tubes filling rooms, generating lots of heat back in the 50s, 60s, and maybe into the 70s.
Yeah, but I mean, all the experiments were done on mainframes. On these single big computers.
What's a mainframe?
What is it? I mean, geez.
Yeah. Do we know what those are anymore?
Does anyone know? But a centralized single big computer where you may have had multiple terminals plugged into it. As time went on, they had terminal access.
Like racks.
Yeah, and
for one computer.
And you're one big university. You're one university have that one mainframe that your PhD candidates could steal time on.
You could wait for a little computing time
and get their 16K program to run
on punch cards that they lined up.
And then as the years roll on, these things get bigger and bigger and bigger, and we finally see the real split happen in, say, the 80s. And what happened in the 80s, Scott?
Microprocessors, CPUs, the PC really.
Yeah, and at that point, I think what you see is from a history of machine learning is you see quite a few new things come out. And it wasn't just thinking changed and computation became available in the form of the PC to quickly try stuff out without, going through these elaborate, chain of...
You could spend $5,000, which is a lot of money at the time, fine, maybe $25K equivalent now or something. But, you could spend that amount of money and now you have your own computer, which is like crazy before.
You're not going to be able to do the same stuff the mainframe could. Yeah. But you could at least try out a lot of ideas rapidly. Rapid prototyping is so huge in every single industry. And so you see big things. You see a lot of big things in reinforcement learning coming out of the 80s. You see a lot of basic stuff in deep learning.
Yeah, the groundwork is being laid then.
In
many, many ways.
But even then, the big computers still don't have what it takes to power what we think of today. And you see as the architectures get more RAM, more compute, you see a steady trickle of more and more stuff come out, I think, from the 80s and through the 90s. And then the 2000s hit and the world changed.
Yeah, Pentium 1, Pentium 2, Pentium 3, that kind of happened throughout the 90s, et cetera. CPUs just kind of got bigger, better, faster, a little more memory. Hard drives got bigger. Clock speeds got faster.
Yep.
And, sort of famously, Moore's Law, et cetera, that stuff happened. But yeah, then into the 2000, late 90s and mid 90s, you have graphics processing units, or GPUs, that start to become made and popular.
Yep.
And then mid 2000s is when NVIDIA, who's actually an investor in DeepGram,
Full disclosure.
But
this was still cool.
Yeah, they started doing CUDA, which is very big. Which is CUDA. If you don't know what it is, it's making it so that a normal programmer could access a GPU and use it to perform tasks in a way that they're used to.
Yeah, C-like interface.
Yeah, so you make a nice interface that's like C, which is a programming language that many programmers know, but then it actually runs on the GPU.
Yep.
And usually what this means is very fast speedups for specific tasks, but those specific tasks are like matrix operations and things that are massively parallel.
Yes, and you still don't see during that period what we see today, but that's when probably the big research, academics started taking notice, and like you're starting to see the beginnings of papers talking about GPUs and how it can speed up machine learning. It had been done in the 90s using GPU-like processors. It had been done throughout the 2000s, but it just never caught, because every single time it was
hard.
It's really hard. It's really specialized. They change the hardware out, and all your stuff breaks.
And now you have to be a machine learning expert, a data expert, a software expert, and a hardware expert in order to do any of it.
And a certain number of experts you break.
Yeah. It's too many experts.
I ran out of fingers to be an expert on.
Yeah.
But CUDA was just a game changer.
Yeah.
And by the late 2000s, early 2010s, we are starting to see an explosion of machine learning stuff coming out, because just like when the PC came out, you no longer needed this huge server of 1,000 cores to be able to do anything in a reasonable amount of time. Now you can go to your desktop and bust out a reasonably priced graphics card, and you can do amazing things. You can start recognizing cats. And once you can recognize cats,
well, people are excited then.
You're excited then.
Yeah, you identify the cat neuron.
Yeah, the cat neuron.
Yeah.
And you can do a rapid prototyping. You've got a great, crazy idea. You don't have to write up a 15-page, report on what you think you might gain out of this, so that you can borrow a bunch of time on a huge
just go
cluster.
do it. Maybe a day or two later.
Yeah, and it works
answer.
or it doesn't. It's enough to go forward on.
Yeah.
And so you just see this massive explosion around there.
Yeah. So we're in particular talking about the deep learning side of machine learning, but there was machine learning going on before deep learning.
Oh, yeah.
That's true.
Deep learning is a little subset of machine learning.
Yep.
Not a little. It's a big subset.
A lot of hype, a lot of money dumped into it, but a lot of promising things, especially on the perception side, like being able to see or understand or whatever, those types of things. Deep learning is pretty successcul at. But there are other types like decision trees and boosted decision trees and other machine learning types that have been around for the 80s or earlier, that you could do on CPUs, and actually very fast, right? You can train them, they're very quick. You can do tests. You can actually dissect them and figure out why they made their decisions in a lot of ways. But they usually aren't as good. Yeah. And then people started to get really excited about GPUs and deep learning because, hey, once you throw enough data and compute and deep learningness at something, then it can
figure out your loss function and get some basic structure going.
Yeah, get some basic structure going. Then it's like, wait a minute, things are starting to work really well. And this is like late 2000s, early 2010s. Yeah.
And you see that you see it on image recognition tasks. You see like the accuracy just being amazing, like error rates dropping like this, and it's all right around that time. And it was people being able to try so many ideas and being able to have access to the compute to train these models and test these things out. It's not that suddenly brand new ideas magically appeared out of nowhere. It's the ideas that everybody wanted to do. It just took them a long time to do. They were finally able to rip through.
This is why the infrastructure is so important to you. You finally got all your stuff together. Your hard drives are big enough. Your memory is large enough. Your memory bandwidth is fast enough. Your computation speed is fast enough. The number of flops that you can do is enough.
And the tools.
Yeah.
And this is again the big thing. Like CUDA, and it has enabled a huge set of tools.
Yeah. There are layers upon layers here, where it's like, hey, there's a GPU that has hardware stuff going on inside it, but then that is abstracted away by CUDA, but then CUDA is abstracted away by other deep learning frameworks as well.
And that just enables the next round and the next round.
It just takes a cognitive load off the person who's trying to develop something. They can be like, hey, I'm going to spin up this thing. I don't even necessarily need to know how it works under the hood, but I can make it do stuff.
It's one less expert finger you need to have.
Yeah,
exactly. I used to have all 10 expert fingers, and then slowly you strip them away. It's like, okay.
Well, now you can make progress in the one or two areas.
Exactly, and you can delve deep, and it's like, I just don't care as much about those other things. I want to care about this problem right here. So it's been an amazing roller coaster ride. But
this is like the training side, though, right?
Yeah. Well, yeah, exactly. We're seeing a shift.
Yeah.
Right. So you're right. The training side has been here. Production side has not. There's not a tremendous production push on the GPU side in a lot of areas until recently.
Yeah. Until very recently.
But that's part of the shift we're starting to see is...
Well, I think the inference side, which is like the production serving of this of these models, that lags behind because the training has to happen. Your models have to work. You have to get comfortable with how they work. And then you think about, oh, maybe I should turn this into a product. And it takes a little while.
Yeah. But yeah, so that was up till, the early 2010s, mid 2010s, and now we're in the later 2010s. And what are we seeing? I think we're seeing another architecture shift. What do you think? What's your take? Are we seeing another architecture shift? What do you think is going on?
Well, I
here?
think like the AI chip in the iPhone. People have heard about that. Where you can, what do they call it? AI kit or ML kit? I think.
Yeah.
ML kit. You can use ML kit to do stuff on the iPhone, and it's not using the CPU ananymore, or it's using a lot less CPU.
Apple opened it up to other developers before they. I think this was all enclosed, and they had access to it. Now, now they've opened up.
Anybody,
that new iPhone.
Any developer could go and try and use this chip to do something.
Yeah,
and have it.
But that's the trend. Is first we had no specialized processing, and then we found the graphics world does a lot of what we need. Those big matrix multiplications.
Yeah, it's something we kind of glossed over. But the GPU, why are GPUs so good?
Yeah. Oh, yeah. Exactly. So GPUs do the same operations that it takes to take a 3D scene and rotate it around and do all these special effects there.
Yeah, so like if you're gaming, you see 3D and the guy shoots this or the plane flies here or whatever, this all has to be generated in a virtual world, and there are all the polygons and points, but then it has to be projected onto your 2D screen.
Yep, exactly. Those same calculations. That matrix math is also at the core of most deep learning at the moment, and so deep learning has jumped and adapted itself towards that GPU world that was in the 3D rendering world.
Yeah, scientists were using CPUs and they're sitting there waiting, patiently tapping their fingers, saying like, oh, this is taking a long time using CPUs. And then they look out and say like, what else is going on in the world? Is there anything fast out there? Is there anything that's like massively parallel by any chance? Because the operations that we're doing could be parallelized. And then they see GPUs and like, wait a minute, we should be using those.
Why not?
Yeah, why not? And it takes a while to sort of migrate over, but once you see the first little nibbles of it actually working, then it kind of the floodgates open.
The first time you go and say, well, let's see what happens here. 70 times faster than what I was doing before. I think we've got something we want to spend more time on.
Yeah. Yeah.
And it's only going to get better.
There's this concept for deep learning and machine learning scientists that are trying to figure out a solution to a problem. You're mostly patience limited.
Yeah.
And it's like, you can only wait a few days or maybe weeks if you're really patient, or maybe months if you're really sure it's going to turn into something good. But you can't wait that long to get an answer to your experiment.
Exactly.
And so any speed up you can get, even 2x, you're happy about. 10x, you're really happy about. Some 10x, 50x, 70x on a GPU, you're just like, what?
Yeah.
This enables so much more.
Yeah, it wasn't just one order of magnitude better; it was multiple orders of magnitude better, and that did it. But that brings the point, though. When machine learning came to the GPU, it wasn't the GPU came to the machine learning. I think now what we're seeing is with these specialized integrated circuits, we're seeing hardware is coming to machine learning for the first time.
Yeah.
So, machine learning adapted to the hardware. Now the hardware, we're starting to see it because it's so big and having such an impact. We're really starting to see the hardware adapt to machine learning.
Yeah.
And that's the revolution that's going on right now. It's kind of, everybody knows it, but not too many people are really stating that sea change. Your phone's got specialized logic in it. We're starting to see chip manufacturers really, really make this a major design priority, as opposed to some little secondary thing. And that's a big deal.
Yeah, it's hard. It's a big expense. It's a big gamble, risk, to say, hey, I'm going to build a specialized chip for this thing over here. I'm going to take 3 years and develop it and spend many millions of dollars. The ground might shift underneath me, because machine learning, deep learning, everything is moving at such a fast pace that maybe 3 years from now, the thing I'm building isn't even going to matter.
Maybe.
But people have seen over the past 5 years or so, CNNs are a thing, convolutional neural networks, recurrent neural networks are a thing. For the most part, the these MLKit type chips really focus on the CNN, making that good because this is like image processing from like ImageNet and running those things. But nevertheless, it's like, hey, these typical tasks, I can build those and I can make them fast and I can accelerate them here rather than doing it on a CPU or having to put a GPU, kind of the middle version of it in there. Hey, it's not a CPU. GPU is a lot faster, maybe uses some power, but then I can put it on this special chip and actually get a result out of it. People have actually, people meaning companies like Apple, have actually put their money down and said, okay, we're going to go after that.
Yeah. There's a lot of big things. I mean, it really comes down to it shows maturity. And it shows that we have enough examples floating around of what it takes to do this stuff, to understand how do we need to access memory that's different than how you do it with that generic GPU. I shouldn't say generic GPU world, but the specialized GPU world.
It feels generic now because things have been working for years now, and but if you went back 5 years ago, you'd be like, whoa, it's all kind of is this actually going to work or whatever? 5 years later, we're like,
it's out of the box now.
Fine, just buy one, you pop it in.
But so we now have a much better understanding of the specialized hardware environment that machine learning, deep neural networks, and that kind of world is imposing on this hardware. And the money's there, the knowledge is there. There's still risk. I don't think anyone doubts that we're going to see major shifts in how machine learning works and all that. But these are the first stabs, and the first stabs are making huge improvements. Low powered, machine learning chips sitting in your iPhone, enabling, amazing new things, Can you do real-time voice? Can you do real-time image recognition? The whole augmented reality world has got to be, just having a field day with the ability to do real-time image recognition with these things. It's going to enable a powerful new class of applications, or it already has enabled powerful new classes of applications. And that's direct result of making those specialized hardware bits, and this is just a natural a natural progression. We saw this
Yeah.
like hard drives, back in the old days, the CPU literally would have to tell them to move exactly one place or another. And then you got controllers that started taking that logic off. And then you had whole IO subsystems, and then, specialized and specialized and specialized. And you get big gains from that, but you had to have that knowledge base beforehand to figure out how to specialize correctly.
Yep.
And we're starting to see that now. It's a pretty cool thing.
Yeah. Not everything is happening on your mobile phone, though. You're not usually training networks there. You're not. It might just be the inference, and it's doing inference only for you locally. Added up over everybody's mobile phone, maybe that's a lot of inference power, but still, it's not going to do other things like it's cloud-based or in your browser when you're surfing a web page or something like that. These things are all places where the computation can happen, and the CPU on your laptop has a certain amount of power and computational ability and memory available to it, and a computer in the cloud usually has more, and then on your phone it's less usually. Yeah.
But it is interesting on the browser front. I mean, we're seeing a lot of great tools start hitting on the browser front. JavaScript APIs for machine learning are coming out. And when I say for machine learning, like you said, it's more for the inference side.
Yeah.
You're gonna do your heavy lifting on a box that's got some
you
nice
do your training on a server,
and all this stuff.
Yeah.
And then you make sure it can run on the browser to,
and then maybe you shrink it down,
because I mean, if you're doing it locally in a browser, you probably only need to recognize one stream of audio.
Yep.
You only need to recognize one image. You're not doing 10,000 streams simultaneously. But it's just amazing to see how quickly we've gone and how much we're now specializing and how big this is. It's making hardware changes. It's carving out a niche in architectures, which is a pretty big deal.
Yeah, for your training, using something that's in the cloud or using on premise, like large machine, power hungry, that makes a lot of sense. But also on the inference side, when you need to have data access to a database, basically, right? So it's like if your phone is trying to do some inference on a chip, but then it has to go out and access a database on a server somewhere else in order to like do the inference, it doesn't make that much sense. What it would rather do probably is like just ship off the image and have that handled somewhere else and then get the answer back.
That's true, but that's a great point. You want to put the processing power the data's at.
Yeah.
Because even though we've got big pipes, they may not be perfect. And so you see that trend. We're pushing tools onto the phones. We're pushing that. But there's one area that is growing in leaps and bounds right now that's a big deal at, and that's the self-driving car world. Autonomous vehicles. You can't process that on the cloud.
Yeah, you don't want. Yeah, if your internet connection goes down, you don't want your car to just like stop driving.
It's like, I'm sorry, we can't drive you to grandma's house.
Yeah,
and again,
the buffering graphic comes up.
But there's a turn.
Yeah,
please connect it. There's a turn.
Buffering.
Please stand by.
Yeah,
but no. So you're saying just like on the phone front, you're really starting to see specialized hardware come out. I mean, big time. I mean, NVIDIA's got a great platform for that.
Yeah.
Trying to standardize hardware and all that for doing those big problems locally.
Because you have you have tons of sensors essentially, and you need to have like a rack to mount everything to, and so it's like just get this thing, and then now you essentially have an autonomous car.
And it's key to kind of standardize the interface there, right?
This is still more like a development kit, though, right? This isn't like go buy this, put it on your car, now your car is going to go drive itself. This is something for this
is like buying buying your PC. It doesn't mean that you can do anything with it. It just means that you've got the
you have the hardware
necessary to do cool things with it.
Yeah,
but the point is,
still a lot of massaging that needs to happen.
Specializing hardware for the machine learning applications, and no longer we're kind of borrowing and stealing from the graphics world, and the graphics world's like, okay, we'll make a little concession for you.
Yeah.
Now it's like full blown big deal making specialized stuff for it, which is a huge sea change. It's a huge big deal. But so is this what we're gonna see, or what do you think about this, Scott? Is this like, where are we at in are we on the right path, or is this going to be what we see 10 years from now? Or
I think the time scale of 10 years, maybe there could be a change, but that's a long time away.
Yeah, in internet year and in
deep learning years, like that's a long time away. But I think talking about the different types of devices matters. So, like mobile, personal computer and server, that matters. But also if you're talking about training or inference, I think it matters. It's going to be hard to get away from GPUs in the server domain, just because power isn't so much of an issue there. And you really want, you want raw, high functioning power that is very agile. So you can do your experiments like, hey, I have an idea and it needs to access a whole bunch of memory and shift this around, and it needs some transformation that's done on my CPU, and then I'm going to ship it back and I'm going to do all these things. You need that flexibility essentially. If you're going to have a, really hard coded AI training chip, then you better not change your model very much.
Yeah, exactly.
Yeah.
You better not bring in brand new crazy concepts.
Yeah.
You better not bring in brand new ideas. You better stick to large numbers times large numbers plus large numbers.
Exactly. And you can train your ImageNet model really fast, fine, right?
Yeah.
And
that's so 2000s.
Yeah. Exactly. Great, good for you, But if you're trying to do something more complicated, then you're probably not going to be able to, like time delaying your neurons or something. Like that's not going to happen on that chip, right?
No.
But you probably can do it in a more flexible architecture. Maybe it'll be easier to do on CPUs, hard and time consuming to train, but then morph it to a GPU land where, hey, it can actually grow up a little bit there, and then maybe you ship it off to that AI chip.
I totally 100% agree with you. And for those that don't know, Scott and I have had this kind of running debate. Is like, what is this? What is the future of machine learning like? And one of my first shots across the bow with Scott was the whole matrix math, 10,000 wide, whatever. I think that we're going to see, much incredibly more complex and fine-grained structures come out that are not as compatible with today's, efficient large matrix multiplication.
Yeah, right now the idea is take whatever problem you have and think really hard so that you can shoehorn it into doing a matrix multiplication.
Yeah.
And if you can do that, then it'll probably be fast enough in order to train, and you can see the result.
Yeah, and we've taken a brand new big huge resource area of all this compute that GPUs have given us, and like I said, we've adapted to that, and now that we're seeing the hardware adapt to us. Back in the machine learning world, I think we're going to see an explosion of new architectural ideas. There's a lot more revived interest in and thinking about the basic, structure, basic neurons, going back to biology again and pulling in new things like time delays and stuff like that, pulling in brand new types of ways of connecting them. Again, going down to single connections as opposed to thinking, I've got this 1024 layer and fully connected layer to a 1024 fully connected layer just because it's efficient and fits right in perfectly memory wise and all these different things. It's like, but nothing about the problem said 1024.
Yeah.
Right. Like, how do you appropriately connect these things and get these things together? And again, now that we're merging back and we're having hardware start adapting to us, I think that we're going to start seeing that the current is an iteration 1, but by the time we get to iteration 3, we'll be looking back at the first of them like it can't run anything compared because we've been able to explore these crazy, amazing, brand new, out there,
the
fun
backwards compatibility is not going to be that good.
Yeah, you see this throughout it. Yeah, you make this blind stab into the future, and especially with a field that's changing so rapidly and has so much, so far to go.
Yeah,
it is an impossible task to pick it perfectly. It's amazing. It truly is amazing that we've had as much longevity as we've had with the toolkits, and I think that speaks to the massive power gain that we got from GPUs. It's just such a huge, massive resource that we got that we have kept using it and not shifted it dramatically so far.
But it speaks to how large the problem is too. It's like, hey, we still use the old internet too,
Yeah.
right? And it's like, well, things get better, things whatever, but like it's still using similar protocols that we just kind of beef up over time. And yeah, it's frustrating. It doesn't work as perfectly as you would expect, but hey, it works, and you can make advancements with it. And a similar thing will probably happen over the next 5 or 10 years where it's like, hey, we have all these tools, we have all this established literature and tribal knowledge about how this stuff works, and we keep getting more and more results. But eventually you'll hit some diminishing returns and it'll be like, okay, we need to make a jump to something else.
Yeah, it's an exciting time to be here and see this stuff, and just seeing all the new worlds we can work in. The idea that you can really apply these tools in the browser, you can apply them on your phone, you can apply them on an Internet of Things device, you can apply them on something rolling down the road at 100 miles an hour.
Yeah.
Don't drive at 100 miles an hour, honest.
Never.
Yeah. It's awesome.
Yep. Yep. It's I think, you're going to see it deployed in those areas, server, personal computer, on your phone. You're already seeing it happen, but you're going to see it just integrated more and more. And the inference, especially training, not so much. That's still going to stay in the servers for a while.
Quite a while.
But there's people discuss about like federated training, right? Like using your mobile phone or your CPU or something to train a model, but like very slowly, locally, but then aggregating all the results on a server. Like, hey, that might be a thing, but has not been a thing, even though people have talked about it for a few years.
Well, this is a little off the infrastructure side, but again, going back to these things, these pieces of infrastructure enabling rapid prototyping, we get breakthroughs every once in a while that radically change the playing field. And often what we find is we were doing something incredibly inefficiently before, but because we didn't have the resources to just do that thing fast enough to try the next thing and the next thing and the next thing, it was a huge roadblock. Had we known this one weird trick, we could have done the things in the past.
Yeah. The cost is discovering the trick.
Yeah. And once you find that one weird trick.
Yep.
And so, it's entirely possible that, we're entirely probable.
Yeah.
The next sets of revolutions will come as we find that one weird trick, and it changes everything we know about
absolutely
how networks work and the best way to plug them together.
Yep.
We've got 1/100th the memory, and 1,000 times the speed.
Yep.
Just because of that one weird trick.
Yep. Yep. And one thing I forgot to mention is that you already see some of the GPU side morphing a little bit, saying like, hey, we're going to include FP16 training, which is like a lower precision training, so it can train faster, but while giving up precision. You see tensor cores, that are a more specialized unit instead of just the standard processing unit that they use in the GPUs. Like, hey, here's one specialized just for machine learning, but it's still pretty general. You see the hardware changing on the GPU side as well to kind of get a little closer to that specialization, but without losing the flexibility.
Yeah, like I said, we started off, adapting to the hardware, and now we're seeing the hardware adapt to us. And it's the circle of computer life.
Circle of life. They eat each other too, and they recycle the silicon. Yeah. Okay. Well, that's it for today. Thanks for joining us on the AI Show. What questions do you have about AI? Comment on YouTube or Twitch, or tweet us at DeepGramAI. We are Scott and Susan from DeepGram. We come in peace.
We're certainly not robots.
Definitely not. See you next time.
Ciao all. I'm going to take you down. All right.
I think you already did.
3, 4. Now.